So I mentioned this sphere. Let's imagine that we have a hot sphere, and we decide to drop this hot sphere into a quenching bath. It starts off at TH. It's this uniform temperature. It's been sitting in some oven. We take it out. We put it in this bath at TC. And our job now is to maybe anticipate, just conceptually, what the temperature profile is going to look like inside the sphere. Right? And let's imagine that the bath is big enough that its temperature is not changing. So what would this look like? Let's say what I'm going to do here is plot how to do this. So let's plot the initial temperature. So the initial temperature is this uniform temperature. Let me just do this first. Give myself some guides. Oops. So uniform temperature, initially, that's right here, right? So as a function of radius, my temperature is not dependent, right? There's no change. It's uniform temperature. So this is at what, time equals 0, t equals 0. So shortly after t equals 0, I drop this ball in, and what is the first thing that's going to happen? Right, you're going to start getting heat transfer out from the edges. Does the entire ball go to the bath temperature immediately? No, right? It takes some time. It takes time for this thermal wave to kind of move out. So we want to maybe just look at right on the edge, you're going to have some change in temperature, but internally there's not anything that's been seen yet. Like it hasn't experienced any change. So if we actually plot this out, it might look like, I don't know, it might look something like this. Sorry, let me redraw that a little bit more carefully. So let's say there's this initial kind of drop right at the edges, but internally it hasn't really felt anything. So let's call this at t equals 1. It should make sense just intuitively. You're having heat transfer from the edge, but the middle of it hasn't experienced anything yet. Sort of like you can sort of sense what that feels like. Okay, at t equals 2, now there's been more heat transfer out, but maybe this thermal wave has had time to start propagating in and is bringing down the temperature of the entire thing. So at t equals 2, we can maybe draw it, and it might look something like this. Right? T equals 3, maybe it looks like this. T equals 4, 5, 6. Right, and you can kind of, this should make some sense to you. But the important thing is kind of this difference between the temperature internally and the temperature externally. So in this example, the way I've drawn it, there's this this temperature difference right here. Right, this is, let's call this delta T internal. And then there's this temperature difference right here, delta T external, this temperature difference here. So in the event that delta T internal is a lot smaller than delta T external, pretty much always, this is when the 0D assumption is valid, right? We can basically say, well, I could get away with, instead of modeling this radial temperature profile internally and looking at how that changes with time, what if I just said, well, let's call this temperature that, and let's call this temperature that, and so on, right? And where's the error in this? Like, what's wrong with doing this? I mean, it's not that wrong if all you're trying to do is predict the heat transfer out. If you're trying to predict like the difference between the surface temperature and the internal temperature, this is wrong. But if you're just trying to say, okay, Q dot out is some value, you're only going to be off by the difference between that actual delta T external and the TC up to the first blue line that I drew. So it's a matter of like percentage, right? And the BO number is going to tell you the amount of error that's involved, right? So the whole idea is let's come up with a model for the blue lines, because that's easy. And then later on we'll deal with the more complicated one. Questions? okay? All right, so we have the BO number. The BO number tells us how much error is involved in that estimation of heat loss to the surroundings under the assumption of a 0D model. There is another constant, it's a dimensional group, but there's another constant that helps us describe a problem. And that constant is called the lump capacitance time constant. So the idea is that you can compute some estimate, let's call it tau LC, some estimate of the amount of time that it takes the system to respond to a change in the surroundings. So in our example of the ice bath, you have this hot sphere, you drop it in. There's a certain amount of time it's going to take for the internal temperature to start responding. Right? If I look up here, maybe we would call that like T2. We'd call that maybe, come on, T2 here. Right? Maybe that's what we would call like a response. It's sort of like, I don't know, like you go to the doctor's office and they hit your knee, right? That reaction time, the moment that you feel it and sort of your body processes it, that's kind of that reaction time. It's not the full time it takes to swing and come back, it's that little bit of reaction time. That's what tau LC is supposed to represent. It's kind of that initial response time. So tau LC, we can compute that as follows. It's just our surroundings times the capacitance of the object, the thermal capacitance of the object. So let's just note this is resistance to surroundings. This is the thermal capacitance of the object. All right, so let's actually compute this out for an example. So tau LC. For our previous example, we had the convection was the only thing. So that's our resistance. That would be just 1 over HA, 1 over H bar AS. The capacitance of the object, right? This is how much energy the object can hold per change in temperature. And so that would be mass, M, times specific heat, C. Right? So MC over H bar AS is a good estimate of the amount of time. You could convince yourself this works, so we could just go through and do a dimensional analysis. So H bar is watts per meter squared Kelvin. AS is 1 over meters squared. M is kilograms. C is joules per kilogram Kelvin. Right? And if you go through and cross stuff out, meters squared, what else we have? Kilogram, kilogram, Kelvin, Kelvin, joules, and then watts is actually joules per second. Right? You end up with units of second. Right? So the tau LC is actually a time in seconds that you would expect your system to take to respond. Okay. So why do I have a sine wave down here? Well, I want to show you kind of what it looks like to have different time constants, as different values of tau LC, when the surroundings are changing. So let's say, I don't know what an example would be. Let's say like day to day you have your house, or maybe, let's think a really big rock, okay, instead of your house. So a really big rock, day to day is experiencing this oscillation in temperature, right? Like it gets hot in the middle of the day, cold at night. If you were to look at the thermal capacitance of the rock and then look at the resistance to the surroundings, say due to convection, radiation, whatever, we should be able to anticipate whether that rock is actually going to trace along with the daily temperature variation, or whether it's so big, has so much thermal mass that it basically doesn't care, right? So there's these different like scenarios that you can plot out. So the first one would be, let's look at a case where tau LC is much less than this daily variation time period. So let's call this delta T surroundings. So much less than delta T surroundings. So that's saying the amount of time it takes is much less than this time period. The amount of time it takes to react, much less than the time period. So what would this look like? Well, I guess you can imagine it would probably look something like this, right? It's sort of trailing along, maybe it lags a little bit. but it basically trails along with the ambient temperature. Right, so that's this one here. What would it look like if we had a scenario where tau LC was much larger? Tau LC much larger than delta T surroundings. In this case, you're going to see some effect, right? I mean, usually you'll see some effect. That effect is going to be muted, right? It's not going to see this extreme variation. It doesn't have as much opportunity to respond. So it might look something like this. So it's still oscillating a little bit, but it's very muted and it's lagging, right? There's a big time delay between the peak of one and the peak of the other. All right? So, I mean, hopefully intuitively this makes sense, but what you can do for these types of problems is compute the BO number first, then compute tau LC, and just with that bit of information, you should kind of be able to anticipate what the system's going to do. Right? These are huge clues in your intuition of the problem. Right? Okay, so let's go through some analysis here quickly.